Hi everybody. I hope you're all doing well. We're getting close to the end here. So we've got this is chapter 17 that we're starting today. Chapter 17's relatively short, and we're just going to make it short simply because we don't have a lot of time. We probably wouldn't have spent much time in class on this anyway, so we'll finish the notes for this probably on Wednesday this week. And then the test for this, actually it'll probably only be a notes quiz on this. I think that's the only thing that we're going to really do. We'll see. It'll be a test or a notes quiz, but it'll be on Monday, the week after this. So we've got today notes, we've got Wednesday notes, we've got Friday, we'll probably do some review, maybe an Edpuzzle video or two. And then on Monday next week will be the test or the notes quiz. We'll see which one comes up, okay? So you've got your paper, you've got your calculator, you've got your periodic table, you've got all that good stuff that you should have out in front of you. So we're starting what we would call thermodynamics, okay? So what's the difference between this and everything else we've been doing? Well, at this point, instead of just talking about the substances that are in a chemical reaction, now we're interested in the energy of the chemical reaction. Okay, so this is one of those few times where we cross over a little bit into what we would normally call physics, right? Because physics is the study of energy. So we're going to be talking about the energy of chemical reactions. So this is sort of this crossover. But it is really important because the energy of a chemical reaction sometimes is just as important as the chemical reaction itself. All right, and so we want to be able to talk about that and calculate it and measure it and all that kind of stuff. Okay. We've got to get a few things out of the way first. We've got to get some vocab kind of cleared up. I know you wrote out the vocab and you've done all that already. Okay, but let's just go through and make sure that you understand what these terms all mean. So the part of thermodynamics that we're focusing on is what we would call thermochemistry. So you can see that the term thermo, right, the prefix thermo always means heat. So thermochemistry is the heat changes in a chemical reaction. Work, we're going to mention this term called work. Now I know you've heard the term work before in your life, but in terms of a scientific meaning, right, work in science means a force acting over a distance. Okay, so what does that mean? That means that work is done when something moves. Okay, if you push on something, like for instance, you're moving your pencil or your pen against your paper right now, at least I hope you are. If you're moving your pencil or your pen across the paper, that means that the force that you're providing against your pencil or your pen is causing it to move over a distance. You're doing work, right? If you were to go and kick a soccer ball, you're doing work, right? Because you provided a force and the soccer ball moved over a distance. If you were to go and push something so that it moves, anything, you're doing work. But if you were to push and push and push against something and it never moved, no matter how tired you got from that, no matter how much work you thought you were doing, scientifically you did no work, because if you push something or you pull something and it doesn't go anywhere, then you did no work. Okay. Now, how does this relate to a chemical reaction? Well, if we had a chemical reaction, let's say, that produced gases, and it was producing a gas, and eventually the gas built up and the pressure built up so much that the gas actually moved something or caused something to happen, then the reaction can do work. So we talk about reactions being able to do work. You remember that way back at the beginning of the year, the lab that we did with the baggie, right? And we put all of that stuff in the baggie and you sealed it up, and a lot of you were a little surprised that the baggie eventually popped. Not everybody's did, but some people's did, right? And so the gas that built up inside of there actually did work. It caused that whole system to move, right? The baggie and everything popped open. So that's what we call work. And so when we talk about what energy is in science, right? Energy is specifically the capacity for doing work or supplying heat. And we'll talk about what heat is in a minute. So energy is something that something has that allows it to do work or allows it to supply heat, right? You have energy inside of you because you have the capacity to do some work. You also have the capacity to supply heat, okay? There's two different kinds of energy we're going to talk about in here. There's kinetic energy, which is the energy of movement, and there's potential energy, which is stored energy, right? So kinetic energy would be the energy that's actually being used to cause something to move, and potential energy is just the energy that's being stored by something, okay? So potential energy in the case of a chemical reaction might be the energy stored in the chemical bonds between the atoms, right? That's what we call chemical potential energy. Can you release that energy out of those bonds? Sure. If the bonds get broken and then reformed into new bonds, there might be energy that gets released from that, okay? Oops, there we go. Okay, and then finally, as I talk about heat, right, a lot of people think that heat is temperature, and that's not right. Heat is not temperature, right? We can calculate heat from temperatures. We're going to find out here in a little bit. But heat is not temperature. Heat is the transfer of energy from higher temperature to lower temperature. It's always higher temperature to lower temperature, right? So if you were to take, for instance, your hand, right? If you were to take your hand and you were to put it on top of the desk or table or whatever you're sitting at right now, most likely your hand is much warmer than the table is. And so when you put your hand on the table, you will feel cold. And that feeling of cold is the fact that the heat is moving from your hand, which is higher temperature, to the table, which is lower temperature. Okay? So heat is not energy. Heat is a process, okay, of transferring energy. And it always goes from high temperature to low temperature. You can't stop it. You can slow it down, but you can't stop it, okay? All right, so we have some basic terms here that we're going to be talking about. I just want you to have that kind of in your head when we talk about these terms. Now, when we talk about a chemical process, a chemical reaction, or some kind of substance changing, we talk about it in terms of being the system. Right? So the system is the part of the universe you're focusing on. The surroundings then would be everything else. So for instance, let's say you had a test tube like in this picture. If you had a test tube in this picture and you had some substances inside the test tube, then you're probably interested in what's going on inside the test tube. So that's your system. And everything outside of that, so the air, the actual test tube itself, everything else that's around it, you would all be the surroundings. Technically, the rest of the universe would be the surroundings also, but usually only the immediate area around the system are what we're going to refer to as the surroundings, okay? There is a law of conservation of energy, just like there's a law of conservation of mass, right? Law of conservation of energy says energy cannot be created nor destroyed. You can change it into different forms. So for instance, you might have kinetic energy that gets turned into potential energy, or you get potential energy that gets changed into kinetic energy. Or you could have light energy that's changed into heat energy. Or you could have heat energy that's changed into electrical energy, so on and so forth. There's lots of different kinds of energy. We're not going to talk about them all in here. Again, this is not physics. We're going to keep our focus narrowed to talking about energy of chemical reactions. But I do want you to know that energy can't just come out of nowhere. If you light something on fire, okay, if you light something on fire, the fire is not just a spontaneous amount of energy coming out of something. The energy was already there. You're just releasing it. So if a bomb explodes, the bomb doesn't explode by creating a whole bunch of energy. The energy was already there. The chemical reaction inside the bomb just actually releases all of that energy. Where does the energy come from? Usually it's stored up as the chemical bonds, okay? If we get a chemical reaction in which the heat flows out of the system and into the surroundings, so heat's coming out of what we're looking at, we call that exothermic. And if heat flows into the system from the surroundings, then we call that endothermic. Those should be really easy terms for you to remember. You know therm means heat. And then exo sounds like exit, right? So exothermic, the heat is exiting the system. And endo sounds like enter. So endothermic means the heat is going into, it's entering into the system. So again, where does it come from? Where does it go? In exothermic, if it comes out of the system, then it's got to go to the surroundings. In endothermic, if it's coming from the surroundings, then it goes into the system. So we can put a negative or a positive sign on these if we're talking about numbers, and we're going to talk about numbers here in a minute. Exothermic is a negative heat change. Endothermic is a positive heat change. This is one of the weird things that we start to get into when we get to this chapter, because everything up to this point in chemistry, everything has been positive. We've never dealt with negatives before at this point in chemistry. This is the first time we start to deal with negatives. So we can have a negative heat change or a positive heat change, depending on where the heat is going. If it's leaving the system, it's negative. It's losing it. If the heat's coming in, then it's positive. So these are just little graphics to kind of give you a sense of visually what's happening, right? So if that white square there is the system, then endothermic means the heat is going into the system, and exothermic means heat is coming out of the system. Okay. Now, we can measure heat, and we're going to talk about that in a second, how we do that. But if we were to measure heat, we have to have units for it. Heat can either be measured in calories. You've probably heard that before. That's an old English unit that we still use. Or joules. Joules is the newer SI unit, which we would use probably more often in here, because we try to use the SI system a lot more than we use the old English system in this class. So if you want to convert between joules and calories, they're not the same, obviously. So it takes 4.184 joules to make 1 calorie. Now I do want to say that a calorie is a really small unit of energy, okay? A calorie of energy is a very small unit of energy. And it takes over 4 joules to make up 1 calorie. So you can imagine a joule is even smaller. Now, when we talk about calories, we're not talking about the same calories that you're used to thinking about. Right? When you think of calories, you think of the calories in your food. And food calories and the calories we talk about in science are actually 2 different things. A food calorie, capital C calorie, is not the same as a regular calorie that we're going to be talking about. In fact, it's 1,000 of those calories. It's what we would call a kilocalorie if we were talking about the metric system. So a food calorie and a regular calorie are not the same thing. So just keep that in mind, that food calories are 1,000 times the calories we're talking about. So the calories that we're talking about here in science, again, are really small amounts of energy. Now, if we wanted to measure heat, and we have a little bit of a problem. Measuring the heat of something requires that you measure the temperature of it. But remember I said before, heat is not temperature. Heat is the transfer of energy between things that have different temperatures. So what if we wanted to measure how much heat something needed before its temperature went up. Well, you could do that. That's called heat capacity. Right? So it says here heat capacity is the amount of heat needed to increase the temperature of an object exactly 1 degree Celsius. Okay? There's one little issue with this, right? It's dependent on how much you have. It's dependent on mass and chemical composition, what it's made out of. So if you took a substance and you wanted to compare it to another substance, and you wanted to see which one had the higher heat capacity or the lower heat capacity, you would have to make sure that they have the same mass. So it turns out that this is not the most useful way of thinking about heat. Right? So again, heat capacity is heat divided by temperature. So heat is calories or joules divided by temperature, which is usually degrees Celsius. Could be Kelvin, right? So the more useful way of looking at heat capacity is something we would call specific heat capacity. And the reason why this is better and it's something we use more often is because we're going to say everything has the same mass that we're comparing. So specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of that substance, 1 degree Celsius. So now we take mass out of this. It's all 1 gram always. Okay, so this is only dependent on what it's made out of. So if we looked at a comparison, here's a table of heat capacities. These are specific heat capacities, actually. Specific heat capacities of different materials. And you can see that this allows you to tell which substances can actually take in more heat before their temperatures go up. Look at where water is on this. Water is really high. Only ammonia is higher on this list. Water has a specific heat capacity of 1 calorie per gram degree Celsius. In other words, if you took 1 gram of water and you wanted that water to go up 1 degree Celsius, you'd have to give it 1 calorie of energy. And you're thinking, well, you said a calorie is really small, so that's not very impressive. But remember, that's 1 gram of water. That's very, very little. It's like 10 drops of water. So if you wanted 10 drops of water to go up just 1 degree Celsius, you have to give it 1 calorie. But look at something like copper. Look at copper on this list, 0.09. So 0.09 calories, that's 9/100ths of a calorie, can take 1 gram of copper and raise it 1 degree Celsius. So you need a lot less energy to heat up copper than you do water. Water's really good at storing heat. Okay. So how do we calculate specific heat capacity? Okay, so specific heat capacity, which is abbreviated C, is equal to heat, which we're going to abbreviate Q. And I know you're like, wait a minute, that doesn't make any sense. Well, we're going to use H for something different here in a little bit. So we can't use H for heat here. So we had to use a letter that we don't use very often, so we picked Q. So specific heat capacity, which is C, is equal to heat, which is Q, divided by mass, which is M, times, that's not X, that's a time sign, sorry. That's a times the change in temperature. So the delta symbol in math means change in, so it's change in temperature, that's the T. And change in temperature always means final temperature minus initial temperature. Okay? So this equation here is going to be really important for us, because here's what it's going to allow us to do. In its current form, we could calculate specific heat capacity. But what if we already know the specific heat capacity? Like in this table here, you already see the specific heat capacity of water. You already know that. What if we wanted to solve for Q instead? What if we wanted to know how much heat it took to do this? So we could rearrange this equation. I want to get Q by itself. The M and the delta T are on the bottom here, so I'm going to have to multiply them to the other side. So Q, the heat, is equal to the specific heat capacity times the mass times the change in temperature. Now, a lot of times, just to make it easy to remember, a lot of people will write it in this order instead. When you write it in this order, it kind of looks like it spells out the word MCAT. And so a lot of times we'll just remember this equation. Q equals MCAT. And so it's easy to remember, and it's something that you do need to remember because we do use this quite often when we talk about the energy in chemical reactions. So the heat, the energy in a chemical reaction can be calculated using this equation. What's the mass of the substance? What's the specific heat capacity of the substance? And what's the change in temperature of the substance? Okay, so that's really useful. We're going to do some work with that. So let's try a practice problem. I have a piece of stainless steel. It weighs 1.55 grams and it absorbs 141 joules of heat, while its temperature increases by 178 degrees Celsius. It wants to know what's the specific heat capacity of the stainless steel. So let's go through and figure out what we know. It says 1.55 grams. Well, we know grams is mass. It says 141 joules. We know joules is heat, so that's Q. It says the temperature increases by 178 degrees Celsius. Well, that's a temperature. And it says that it increases by that amount, so that's our change in temperature. And then finally, it's asking, what's the specific heat capacity? Well, that's C. That's what we don't know. So now we have our knowns and our unknowns. So let's write that out, right? We have C, which is our unknown, equals Q, which is 141 joules, divided by M, which is 1.55 grams, times delta T, which is positive 178 degrees Celsius, because the temperature increases by that amount, so it must be a positive number. And so if we calculate that, we do it in our calculator, 141 divided by 1.55 times 178, we get 0.511. And the units would be, since nothing cancels, it would be joules over grams degrees Celsius. Okay. So that's just one way that we can use that equation, just one example of how to use that equation. Now, in real life, if we wanted to actually do this, let's say we wanted to measure the specific heat capacity of that stainless steel, right? How in the world would we be able to do all of that? Well, you have to do it in a controlled environment. Remember, you've got heat all over the place. I want to know just the heat inside of one thing. I'm going to have to keep it separated from everything else in the surroundings. So this is a process we call calorimetry. You can see the calor at the beginning there. It usually means hot or heat, right? So calorimetry, and rimetry, that's the metric is the measuring of it. So this is the measure of heat. So calorimetry is the measure of heat. And here's one thing we always remember. Law of conservation of energy says, whatever heat gets released by one thing must get absorbed by another thing. Right? You're giving off heat right now to the room you're sitting in. That means that you are technically getting cooler and the air around you is getting warmer. Now, if you never produced any of your own heat again, you would eventually cool down to a certain temperature. The air around you would heat up to a certain temperature, and you would eventually become the same temperature. But you keep producing more heat because you have a chemical reaction always happening inside of you producing heat. Okay? So we know heat released equals heat absorbed. So if we were to take and put, let's say, what we're trying to measure the heat of in something that was controlled, like, I don't know, an insulated container, right? Then we could actually measure the heat change using that equation we just learned from above, Q equals MCAT. Now, most of the time, we're going to be using something called a calorimeter. So a calorimeter is a device that allows us to do calorimetry, measure heat change. It takes place at constant pressure inside of a regular room. And so anytime we have a change of heat for a system at a constant pressure, instead of calling it heat, we technically call it enthalpy. All right, so here's where the H went from before. The change in heat for a system is delta H. Now, why don't we just continue to use Q, or why didn't we just use H originally and stop with all these extra words? Well, there are some technical differences between enthalpy and heat, but for our purposes here, right, in most of our situations that we're going to be talking about in this class, delta H and Q are basically the same thing. So if we wanted to use Q equals MCAT, but we want to use that with a chemical reaction, we basically could. All right, so what's a calorimeter and what's it look like and how is it made, right? So a calorimeter is used to measure the heat change in a chemical system. We are generally going to have this set up like you see here. We're going to have some kind of insulated container. Could be as simple as a coffee cup, or it could be a thermos, or it could be a cooler like you keep drinks in, right? There's a lot of insulated containers out there. So you have an insulated container, and a lot of times we're going to put water inside of that container. Now, why would we put water in there? Well, first of all, water is a really good absorber of heat. We saw the heat capacity of water was pretty high. And second of all, we know exactly what the specific heat capacity of water is. It's 4.18 joules per gram degree Celsius. Or as we learned earlier, it's 1 calorie per gram degree Celsius. So it's a number that we all know, so it's easy since we already know what the specific heat capacity is. Then all we need to know is what's the mass of the water, what's the change in temperature of the water. And we put it in an insulated container because we don't want heat from other surrounding things to mess up our measurements. So the heat change from the system, the enthalpy change of the system, is equal to the opposite of the heat change of the surroundings, right? So if the system's heat goes up, then it must have got it from the surroundings. And we're going to make sure that water is the only surroundings that we have. And since we know what water's specific heat capacity is, we can calculate the heat of whatever we put in the water. This is the kind of calorimeter we would use in class if we were actually doing a lab. It's a really simple device. It's 2 styrofoam coffee cups inside of each other. It makes for a nice little insulated system. That way the heat of the room, the heat of you, the heat of things around the cup could not get into it, and the heat that's happening inside the cup couldn't get out. So the only heat change we're going to have is between the water inside that coffee cup and whatever we put in the water. So we would just need to know how much water did we put in there, how many grams was it, and we need to know the change in temperature of the water. So that's why there's a thermometer in the water, right? Now, you can also do calorimetry in something a little more advanced, in something called a bomb calorimeter. And I know you're looking at that word going, bomb? You mean it's going to explode? No, that's not what bomb means. Turns out that bomb simply means an increase in pressure. So a bomb calorimeter is a little more advanced because we have one section inside of another section, and it's not open to the outside air. This is what they use to measure the heat that is in your food, for instance. If you ever wondered, if you were looking at the side of your cereal box one day and you're like, oh, my Fruit Loops, it says it's 200 calories per serving. How do they know how many calories of energy I'm going to get from my Fruit Loops? This is how they do it. they can put Fruit Loops inside of that little yellow bowl there in the middle. You notice how the yellow bowl has some wires around there. The wires are hooked up to a high-powered source, so when they turn it on, it's kind of like heating up the wires in your toaster, right? So it can basically ignite whatever food is in there, cause it to catch on fire. So they actually burn the Fruit Loops. And then, and the Fruit Loops are in here, and they're burning, they're giving off heat, right? And the heat eventually gets into the water that's surrounding this whole thing. And the water's temperature is going to start to go up. And if you know how much water is here, and you know how much its temperature goes up, and you know the specific heat capacity of water, you can calculate how much heat came off of your Fruit Loops. Now I know what you're saying. You're saying, well, when I eat Fruit Loops, I'm not burning them. You're right, you're not burning them, you're digesting them. But it turns out that digesting something and burning it is doing the same thing, right? You're breaking the bonds inside of those Fruit Loops. And therefore, you're doing the exact same thing. That's where you get your energy from. All right, so we can get a pretty good sense of how much energy you're going to get out of your food simply by burning it. Now, it doesn't matter what kind of calorimeter we're talking about. It doesn't matter if we're talking about a bomb calorimeter or a coffee cup calorimeter or whatever. They all work basically the same way. So let's do an example of how this would be used to calculate the heat. Let's say we have a coffee cup, a foam cup calorimeter, and we have some water in it, 25 milliliters of water at 25 degrees Celsius, that's room temperature. And we take a small pebble and we heat it up so that it's really hot. And then we throw it in that water inside that coffee cup calorimeter. Now, you know, even before you got to this class, if you took a really hot rock and you put it in some colder water, what will happen to the hot rock? Well, the hot rock's going to start to cool down. What's going to happen to the water? The water's going to start to heat up. Eventually, they're going to reach what we call thermal equilibrium. They're going to come to the same temperature. So it says the water here reaches a maximum temperature of 26.4 degrees Celsius. So how many joules of heat were released by the pebble? Now, we don't know anything else about the pebble. We don't know what temperature the pebble got to. I don't know how big the pebble is. But I don't need to know all of that, because I know whatever energy came off of the pebble must have gone into the water. And I know all sorts of things about the water, right? So whatever heat that the water gained has to be equal to the heat that the pebble lost, all right? So the heat that the water gained, so that's basically Q, right? Enthalpy and Q are basically the same thing, so Q equals MCAT. So the heat that the water gained is the mass of the water times the change in temperature of the water times the specific heat of the water. So it's 25 grams of water, specific heat water is 4.184 joules per gram degree Celsius. And what was the change in temperature of the water? Well, the water started off at 25, it went up to 26.4, so it went up 1.4 degrees. So if you were to calculate that, you get 146. So the grams would cancel, the degrees Celsius would cancel, you'd be left with just joules. So the change in heat of the water is positive 146 joules. The water gained 146 joules. Where did it get it from? It must have got it from the pebble. So if the question is, how many joules of heat were released by the pebble, it must be exactly opposite of that. All right, the change in heat of the pebble is equal to negative 146 joules. This is how a calorimeter is useful to us, right? Because it allows us to calculate the change in the heat of the water. And then if we want to know what was in the water, what happened to its heat, we just take the opposite, okay? All right, last thing. How do we write all of this out in a chemical reaction? So before, when we wrote chemical reactions, for instance, like this one, we would have written the CaO plus H2O yields CaOH2, and we would have stopped there. But now we're interested in knowing how much heat change is there in a chemical reaction. So we're going to add to our chemical reactions, our chemical equations, we're going to add how much heat change there is. And you notice this one says that there's 65.2 kilojoules of heat as a product. Now, if it's a product, that means that it's being released, right? It's making that heat go out at the end. So we say that this reaction is exothermic because there's 65.2 kilojoules of heat that are given off. So heat is a product of this reaction. We could have also written that the delta H of this reaction is negative 65.2 kilojoules because it's exothermic. If you saw a reaction like this, however, where the kilojoules were written at the beginning on the reactant side, that means that the kilojoules must be taken in at the beginning of this reaction. So this must be an endothermic reaction. 129 kilojoules of heat are being absorbed. The heat is a reactant. So the delta H of this reaction is positive 129 kilojoules. So if you're visualizing this, exothermic, right? Exothermic always starts with reactants up at some higher energy. And then when it gets to the products, notice the products are down here at a lower energy. So there was a drop in the amount of energy. Where did the energy go? It was given off. So that's why we say it's a negative. But in an exothermic or an endothermic reaction, reactants' energies start here, and the products' energies are actually really high. And so there is a gain in energy. So that's why we see these are positive. Endothermic are positive changes in heat. Okay? Now, which out of these two, which one do you think happens most often in nature? Right? Do things give off heat more often, or do they take in heat more often? Do they feel hot to you, or do they feel cold to you? I think most of us would agree that most chemical reactions that we've ever seen in our entire lives probably give off heat. Right? If I were to have you name a chemical reaction right now, I'd be like, oh yeah, something burning or something exploding. Well, those are all exothermic reactions. So exothermic is much more likely to happen. Okay, that's what we call a heat of a reaction. And heat is dependent on amounts, right? So that means that delta H is also affected by the stoichiometry of the reaction. If the reaction has 1 mole of something in it, but you wanted to know how much heat there would be for 2 moles in that reaction, then you'd have to multiply the delta H by 2. Okay? All right, we're going to get into the rest of this stuff on Wednesday. We'll kind of finish up chapter 17 on Wednesday. And then, like I said, we'll do a review on Friday, and Monday will be the tester quiz. Okay? Work on the problems, and I will talk to you on Wednesday.